So in this question, we have a free fall. We'll take a deep dive into a free falls problem where we have something that is going to be dropped. As we examine the information given, we are told that there's a 24 kilogram rock that's dropped. Well, the fact that it's 24 kilograms is irrelevant. It is not significant. Now, we saw this in the Brian Cox video, that it doesn't matter whether it's a bowling ball or an ostrich feather. It doesn't matter what the mass of the object is. The mass is irrelevant in terms of the acceleration. So that's a distraction. We know that it is a 100 kilometer cliff, and we are asked to find out when it will hit the ground. So that is a time equal. This is our delta z. And we want to know eventually what the impact velocity is, the v. Well, let's take a quick run at this by making a diagram. And our diagram, we have a 100-meter cliff, and there is a rock that's being dropped, and it's going to hit the ground at some point in time. It's going to take some amount of time. We're not exactly sure yet. Let's start off, and a good way to start might be with 5 seconds. So 0, 1, 2, 3, 4, 5. Now, since this thing is free falling, we have acceleration. And the acceleration caused by gravity is -10. And it's a constant -10. Gravity doesn't change over that interval, not in an appreciable way. And since it's dropped, that means that v0 equals 0. So our initial velocity is 0. And that means that the velocity after 1 second is -10, then -20, -30, -40, -50. Now, how we got this number is we're actually using this equation, v equals at plus v0. The acceleration is -10, and the initial velocity is 0, so v equals -10t. We're just taking these two numbers and multiplying them together. But we didn't need a formula for that. We just understand that's what acceleration is. The velocity changes by 10 meters per second every second. Next, we will look at the average velocity. Well, at time 0, no time has passed, so having a mean velocity is meaningless. There is no mean velocity. Then we will look at the mean velocity for the first second, and that is going to be -5. And then next we'll look at the mean velocity for the first 2 seconds, and that will be -10. And the first 3 seconds will be -15, the first 4 seconds -20, and the first 5 seconds -25. Now what we are using here is v bar equals v plus v0 over 2. So if we take the last example, we have -50 plus 0 over 2, which is -25, and that indeed is what we get. Again, remember that we can only use this formula if the acceleration is constant. And the acceleration is constant, as we can see. Now, the displacement formula we have is related to average velocity, and average velocity is delta x over delta t. That is always true. So delta x, then, is the average velocity multiplied by the time interval. So the average velocity divided by the time is this column multiplied by that column. Well, 0 times anything is 0. And -5 times 1 is -5. -10 times 2 is -20. -45, -80, -125. And that -125 comes from -25 times 5, because we are multiplying the average velocity times the time to find the displacement. Now, here's what's interesting. We wanted to find out when this rock would hit the ground, and when it hits the ground, it will have a displacement of -100. A displacement of -100 falls in here. And so a displacement of -100 falls in there. And if we look at that more closely, well, it's about 20 to 125. It's about midway. So about midway between 4 and 5 is we're going to estimate it to be about 4.5 seconds. What will the impact velocity be? Well, the velocity at that time will be about halfway as well, and it'll be about -45 meters per second. So notice, using this table, we can answer a lot of questions. We could answer multiple questions. When will it fall 30 meters? When will it fall 70 meters? When will the velocity be 15 meters per second? We can answer all kinds of questions from this table. And for this reason, I recommend that whenever you take a quiz or a test, including the AP exam, on your scrap paper before you even start, is to make this table, construct this table for the first 5 seconds. You'll be able to use it to answer at least one question, if not more. So this is how we can use an average velocity table to arrive at an estimate of the value. Well, what if we want a very precise value? Well, we do what's called an analytical solution. We have two relationships, how velocity relates to time and how position relates to time. Well, when it comes to velocity, we know then the velocity at any instant in time is equal to the acceleration, and for us, that's minus 10. Plus the initial velocity, that was 0. So this equation is our model. It will give us the velocity for any instant in time. And our z equation for the position, z equals 1/2 our acceleration, which is minus 10, plus our initial velocity, which was 0. Now, we want to set up a reference frame and be very particular about our positions. So we know the height is 100 meters. We could establish the top up here as being 0 or the bottom being 0. We know plus is upward and negative is downward, so it's accelerating toward the negative. It is not wrong to establish this is 0, nor is it wrong to establish that is 0. The question is one of convenience, and I can tell you from experience that more often than not, if we set the starting position to equal to 0, will be the easiest. It's not always true, and if there are two objects in place, well then two bodies that would be in motion, it won't be so as clear which one to choose. But we set our starting point equal to 0. What it does for us is, since this is 0, this term drops out. And if we make that 0, that term drops out. And then we're left with a relationship z equals minus 5t squared. A beautifully elegant and simple equation. We now have two models that will give us the position at any instant in time, and another that will give us the velocity at any instant in time. Now, what we want to know is when it hits the ground. Well, when it hits the ground, z is equal to minus 100. So plugging in minus 100, we get t squared is 20. And therefore, t is the square root of 20. And t then is 4.47 seconds. Now, you may wonder, can we leave it as root 20? No. In physics, we always do it out with decimals. We always do it out with decimals. All right? In math class, you can do that, but not in physics. And you don't do that on the AP exam either. You do it out. So the next question is, how many decimal places do we actually use? Because it turns out there are more than 3 digits. Or this doesn't just end at 4.47. We go back to our given. We use 10 for our acceleration. So we use 2 in our acceleration. And we could have used 9.80665. So we could have used up to 6 digits. This 100 is not written by a scientific person, or was written this way on purpose so we can have this conversation, because a scientist would either write 100 point indicating that all three are significant, or they would write 1.0 times 10 to the second, indicating that the uncertainty is in the tens place, or they would just write 1 times 10 to the second, saying they're not even sure if it's 100. Maybe it's 200. Maybe it's closer to 0. So this has 1 sig dig, which is really just an estimate. It's not really a measurement. This one has 2, and this one has 3. So this might have 3. So we should have used a more precise value. We might have used z equals minus 1/2 times 9.8. If we use 3, it would be 9.81. Since this had 3, we might use 4. So it might be 9.807 t squared. So then it would be minus 4.9035 t squared. If we're pulling out our calculator, we might as well be precise, unless it's a multiple choice question. But that's how we would make that determination. If this had 3 significant digits, then we would report 3 here. But given that we use 10, we should probably report 4.5 is the time. So then how do we get the velocity? Well, velocity is minus 10, and we know the time of impact is 4.47 seconds. And you might say, well, wait a minute, we rounded it to 4.5. Yes, but we never round until the very last answer. And using 4.5 over here into this equation would be incorrect and has a chance of giving us the wrong answer. So V equals minus 44.7 meters per second, and minus 45 meters per second to two significant digits. Now, if we compare that to our estimate, we had minus 45 and minus 4.5. And the best we could have gotten is another digit, but and notice they perfectly match. If we did use more decimal places, we might have been able to eke out something a little different. We might have ended up with 4.47, 4.48, something like that. But that's the process for getting an analytic solution. Now, we can also look at these. Once we have this model, we can make a graph. Remember that this equation, v equals at plus v0, is the equation of a straight line. And our equation then is v equals minus 10t. So here is v. Now our initial velocity was 0. Our y-intercept is 0, and it has a slope of minus 10. So that is what this graph looks like. The graph over here, z equals minus 5t squared. We have z, and t, our time starts at 0. It is a downward cupped parabola, which looks like this. So what we are looking for concretely is when this value reaches minus 100. And that will be the time, 4.47 seconds. Now, it's not necessary. We could do it algebraically. And when we get more complicated problems, we'll need to use a different solution because we can't just solve it algebraically without using the quadratic formula. So what we can do is go to our graphing calculator, whether it is Desmos or whether it is a TI graphing calculator. And of course, we hope that we have a TI graphing calculator on the exam, is we can write our equation, minus 5t squared. So that is that downward cupped parabola. So even if we didn't know it was a downward cupped parabola, we could graph it. And we know the position of the ground. The position of the ground is minus 100. And if we zoom out, we can see now that the position of the rock being dropped is the red curve, and the position of the ground is minus 100, and we can look for that intersection to determine the time. And as we zoom in, you can see we are now 4.2 seconds, 4.4 seconds. Over here, we're between 4.4. This is 4.5. So we're looking at maybe 4.43 seconds. We could calculate that intercept, 4.472 seconds, by clicking on that point. So you see we can use the graphing calculator. Now, again, it's not necessary when the equation is simple, like minus 5x squared. But if it has that other term in it, then we won't be able to solve it without using the quadratic formula. And so our graphing calculator is our friend in that case. So this is how we go about solving this one-dimensional drop problem using an average velocity table to get estimates. Perfect for multiple choice. Or to do analytic solutions where we can get very precise answers to our questions. In our next installment, we will look at very closely at how we would do the same process if we were throwing it downward.